Hi! It's a good day. Do you know why? Because today you get to learn more calculus. Woo! Let's do this. So I think my intention is daily lessons 132 through 135. We'll see if that changes depending on the length of this. So the first page is just all the theorems in one place. So intermediate value theorem, this should not say copyright here. This would be f of c. Intermediate value theorem is from a while ago. It's saying that if you have a function that's continuous and it starts at one y value and goes to another y value and it touches every value in between, that means there's some place. So if there's an f of c in between f of a and f of b, so a y value in between these two y values, then there's a c in that interval. So what I mean, this is a, this is b. I've got some continuous function. Here's f of a, here's f of b, meaning the y value. If there's some f of c in between here, there's going to be a c in between a and b. Okay, another one, extreme value theorem. So this was pretty recently. If f is continuous on a closed interval, so just continuous again, we don't need anything about differentiable for either one of these two, then f has both an absolute minimum and maximum on that interval. And I'm going to extend this a little bit further. This is not part of the theorem, but the absolute max and the absolute min, you need to check endpoints and critical values. Critical values are any place where the derivative does not exist or equals 0. So what I mean by that is you need to check, like, what is the function value at A? What's the function value at B? What's the function value at the critical values? The largest value is going to be your absolute max. The largest, or I'm sorry, the smallest y value is going to be your absolute min. Next one, this one's pretty recent. If f is continuous on a closed interval and differentiable in the open interval, so continuous and differentiable, same thing here with mean value theorem, and f of a is equal to f of b. So what I mean by that, so we've got some interval from a to b, and I've got some function. Oop, but this one can't be it because I need f of a to equal f of b. How do I fix this? I do that, and then I make a new one. That's what I do. Maybe I've got something like this. A, b. This function is continuous, and f of a equals f of b. We're going to say that's the case. Then there must be at least somewhere where f prime of c is equal to 0, meaning the slope of the tangent is 0. So like up here, I can see that that would probably be the case somewhere up there. Okay, on the next one, there's somewhere, if this is mean value theorem, mean meaning average, we've got a function that's continuous on a closed interval, differentiable in an open interval, then there's at least one number c in AB where f prime of c is equal to f of b minus f of a over b minus a. This is the instantaneous rate of change equals the average rate of change. So this one, where it can have started with the last one. I can make this any type of function I want. But f of a, it's funny, these are pretty close anyway. F of b, if I find the slope of that line, slope of the secant line, somewhere there's a slope of a tangent that's going to be equal to that for some c in AB. Okay, next thing. So that's just reviewing this. Now let's use them. These are the type of questions that you'll see. The rate at which water flows out of a pipe. That's exciting. Okay, water is flowing. That sounds like a rate to me. Is given in gallons per hour. Nice, this is a rate. Is given by the differentiable function r of t. So r of t is a derivative. We're starting out here already where we've got a rate that's given to us, r of t. The table below shows the measure every 3 hours for a 24-hour period. Okay, so I know a couple things here. I know this is a differentiable function. As soon as I know a function is differentiable, it's also continuous. So that's good. That helps us. So now I'm just going to answer some questions. Some will deal with theorems, some will not. Some will be review. Some is just the stuff that we've done recently. This says estimate r prime of 5, including units of indicating units of measure. R prime of 5. As soon as you see this estimate, and you're estimating the slope of a tangent. This is the slope of a tangent in r prime of 5. Slope of the tangent of r at x equals 5, or in this case t is equal to 5. Estimating it will always be the slope of the secant line. So 5 is about right here. I'm choosing a point to the right and a point to the left. So I'm going to say r of 6 minus r of 3 over 6 minus 3, 10.8 minus 10.4 over 3. And you can stop here and you can say that, well, this would be 0.4 over 3. And if you want to see, like, what are the units of measure, I look in the numerator. And so r of 6 is going to be, my dog is biting his paws and it's super loud. I hope no one else is hearing this. And if you are hearing weird noise, that's why. My dog has lots of allergies and he bites his paws. So in the numerator, 0.4, it says gallons per hour. Do you see this? Because this is r of t. This was r of 6, r of 3. So I'm going to say gallons per hour. 6 minus 3 was the time. Hours minus hours is still going to be hour. So I get gallons per hour squared. That's weird, but that's okay. This means I always want at a moment at 5 hours. So I'm estimating the instantaneous rate of change. So I'm saying at 5 to say what r prime of 5 means. The rate of change of the water flowing out of the pipe. Of water flowing out of the pipe. I'm taking this language right from here, the rate at which water flows out of a pipe. I'm taking that language and I'm just writing it down. This is r of t. Is changing at a rate. So this has a rate of change. So I began with a rate of change and I'm finding the rate of change. Is changing at a rate of 0.4 over 3 gallons per hour. If you change this, gallons per hour, or you can say gallons per hour squared. If you wanted to change this and you're like, I really don't like this way, I want to say this is 4 over 30, or I want to say that this is 2 over 15, you can, but there's also no problem leaving it like this. Okay, the next one says, using correct units of measure, find the average rate of change of r of t from 3 to 18. Okay, average rate of change, average rate of change. When I say that, you should be thinking slope of the secant line. F of b minus f of a over b minus a, or in this case, r of 18 minus r of 3 over 18 minus 3. R of 18 is 10.7, r of 3 was 10.4. 18 minus 3 is 15. This would be 0.3 over 15. And again, you could change this and you could say 30 over 150 or reduce this in some way, or 30 over 150. So you have to be really careful if you do that. Or you can just leave it as 0.3 over 15. Make sure that you indicate the correct units of measure. Again, R, the numerator, was up here. So this would be gallons per hour. The 15 was the 18 minus 3, so 18 minus 3, which was just hours. And we did it. You could change this to gallons of hours squared. This is similar if you take physics right now and you're thinking about acceleration is the rate of velocity, and we're going to get there in this class too. And then, so if you're thinking about acceleration is often given in meters per second squared. This is why it's a rate of a rate, or I could say meters per second per second. Here I'm saying gallons per hour per hour. Is there a time as soon as you see something like this? Or is there a time? Must there be a time? Explain if there is a time, something like that. Think theorems. Like there should be a theorem to say that yes, this is the case. This one has r prime is equal to 0. R prime equal to 0. So think about it. Are there any theorems that come to your mind? I'm given r of t. So this isn't going to be intermediate value theorem because there's no value in between. There are two different theorems that you could use. I just take it out. Sorry. One of the theorems is you could have said something about, I don't have that whole list in front of me anymore. I don't know where I'm at. You could have said mean value theorem or Rolle's. If you automatically thought Rolle's, follow me. If you thought mean value theorem, skip ahead, and we're going to go in that direction for a second. Okay, so if you said Rolle's, you would have to say r of t is differentiable. because it's given. We can even say differentiable, therefore continuous, because it's given as differentiable. Given, I'm writing this up here. Differentiable, therefore continuous. This is if we're using rules. And R of 0 equals R of 24. Is that the case? R of 0 is 9.6. R of 24 is 9.6. So since R of 0 and R of 24 are going to be the same, and you might be asking, this says 0 to 24 and these are not included, but yet you're saying R of 0 and R of 24. That's okay, because at the end of this theorem, it says there will be a value of C in the open interval, which is why this is open. So, and R of 0 is 24. So I can say, therefore, by Rolle's theorem, a value of t 0 is less than t is less than 24 such that, that's the such that r prime of t equals 0 exists. Or I can say is guaranteed. So this is enough. I'm just saying, is it true? Yes, it's true. If you used MVT, your explanation would be slightly different. You would still start RT is differentiable and therefore continuous. But the next thing that you would say is this. R of 24 minus R of 0 over 24 minus 0. And then you would actually have to find this. This would be 9.6, 9.6. Oh, sorry, I went in front of my head. 9.6 minus 9.6 is 0 over 24, which is just 0. As MVT can be applied, because R of t is differentiable, therefore continuous. You wouldn't have to write this again, I just kind of wrote it a little bit weird, so I was clarifying. There must be a value where R of 24 minus R of 0 equals R prime of t. We know this is 0. This would be R prime t. Such a value exists. T 0 is less than t is less than 24. I can't stop myself. Of t exists, such as 0 is less than t is less than 24. This kind of looks like a weird looking 4. 0 is less than t is less than 24. Okay, so two different ways that you can do that, but anytime you see, is there some time where that's true, you're going to be writing a theorem of some sort. Did you want to do another one? Hey, me too. Let's do another one. Oh, I found that paper. Okay, the next one. This one says, the total order and transportation cost C of X is measured in dollars of bottles of Pepsi Cola is approximated by this function. Okay, so this one is the number of bottles. So this is not a rate, it's just a function C of X, where X is the order size and number of bottles of Pepsi Cola in hundreds. That seems important later. Answer the following questions. Is there guaranteed a value? So as soon as I see that, I'm thinking, okay, maybe I get to use the theorem of R on this interval such that the average rate of change is equal to C prime. Which one is that? Average rate of change is equal to the instantaneous rate of change. Or I could say the slope of the secant is equal to the slope of the tangent. Average, mean value theorem. So in this one, mean value theorem, for mean value theorem to be applied, what has to be true? Function has to be continuous in the closed interval, differentiable in the open interval. If I'm looking from 0 to 3, and I look at C of X, is there any values where C of X is not continuous? At X equals -3, which is not in this interval, and at X equals 0, Bum, bum, bum. This must be continuous on the closed interval, and c of x is not continuous on the closed interval, as it is not continuous if x equals 0. So I'm going to say c of x is not continuous on 0 is less than or equal to r is less than or equal to 3, as r, or I should say, I should change this to an x because it was talking about a value of r, as x cannot equal 0. Therefore, mean value theorem, so I'm still saying what I know, cannot be applied to guarantee such a value. So I still like dropping some knowledge there. Like, I know that you were talking about MVUT, but it can't be applied. Okay, there wasn't much room there anyway, so it was probably not going to be not true. But look at this one. There's so much room. Hoping that means that we can apply it. Is there a value of r in this interval such that c prime of r is equal to 0? This is one where you can kind of go two directions again. What two theorems could you be thinking about? Rolle's theorem or mean value theorem. So in this one, in both cases for Rolle's and mean value theorem, they both have the first initial two conditions that have to be the case. I need to know, is c of x continuous? We said the only place that it wasn't continuous was at x equals 0. So is it 3 to 6? Is that okay? Yeah. And I'm hoping that it's also differentiable, but I need to do a little bit more work for that. So I'm going to come up here and change c of x just slightly, and I'm going to rewrite it. First, if I distributed this 10,000, do you see how this would become 10,000? And I'm going to rewrite this as x to the negative first power, just so it's easier to take the derivative of. And the other one, this is a little bit harder anyway, so I could just leave this as 10,000 x in the numerator, x plus 3 in the denominator, because I'm going to wind up doing the quotient rule anyway. I could have changed it and done x plus 3 to the negative first power and done the product rule, but either way, both would be a lot of work. So c of x is continuous. Now I'm just trying to figure out, is this differentiable? So somewhere over here, I'm going to find c prime of x. That'd be negative 10,000 x to the negative second. Why did I not give myself very much room? Plus, I'm going to do something that doesn't really look nice, but I'm going to go down here. I'm going to do the quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And then I'm going to make this look a little bit nicer. C prime of x is equal to negative 10,000 over x squared plus, I can just keep this as x plus 3 times 10,000 minus 10,000 x. Okay, I did all of this work, and I can see that x can't be 0 still, x can't be negative 3, but it is differentiable everywhere else. This is enough work for you to be able to say c of x is continuous and c of x is differentiable. Remember, you say on the open interval, so c of x is differentiable. I don't know why I'm turning my paper. On the open interval, or you can say on the interval 3 to 6. Okay, and then c of x is continuous, c of x is differentiable, and then this is where you've got two different paths that you can take. Two roads diverge in a wood. Do you want Rolle's or mean value theorem? That's the less common rendition of that poem, but I'm sure Robert Frost was probably thinking, do I do Rolle's theorem? Do I do mean value theorem? Which one's the road less taken? I don't know, that'll make all the difference. If you're doing Rolle's, you would still use continuous differentiable, but you'd have to say something about c of 6 being equal to c of 3. If you're doing mean value theorem, you'd have to start right away and just say c of x minus c of 3 over 6 minus 3. And then that would be equal to c prime of x. So if you're using mean value theorem, rules over here. This one, you can automatically say MVT applies and then begin work. This one, you have to say this first before rules can be applied. So C of 6, I'm going to put my function in here. I'm going to say that this is 10,000. So I'm putting the original function in. 1 over x plus x over, when you're substituting this in, when you're putting this in your calculator, make sure x plus 3 goes in parentheses. This is kind of going to be a little bit of a crazy graph, I think. I'm going to change my window. I don't even know what to do right now, so I'm just going to start off by guessing and say, well, I'm going to, we're talking about time, so I'm only going to start at like -1 because I want to be able to see the 0 pretty clearly. I don't know, let's go to 50? Again, this is me just taking a guess. This is in hundreds of bottles. We were talking about 10,000 being up here, so what if I just went to 20,000? Is that going to be too much? I don't know. Hey, I can see something's happening. So that was a pretty good guess. Okay, so I did this. This was my original graph. If I wanted to find, I could go to my table if I wanted to. I could say, see if 3 was 8333.3. If I did 6, you have to be careful about doing this because I'm not using 3 places after the decimal. So maybe you want to go here and just make sure that this is the way it goes. So if I go to value at x equals 3, ooh, there's 0.33333. I want to be able to take 3 places after the decimal for accuracy. Okay, there we go. So when I see this, I can say rules applies. In this one, MVT applies. So in this one, C of 6 minus C of 3, we just said that this was 83.333 over this, right? So we 0.333 minus the same thing. I'm going to do this, 0.333. I accidentally put that equals 0. So yes, a value of R is guaranteed. And then we did all of this work and it asks us to actually find it. So if you did this, the next thing that you need to do is just set 0 equal to C prime of x. So in your calculator, we already know what C prime of x is this whole thing over here. We set it equal to 0, where we set this equal to C prime of x. This one isn't too much different. We set 0 equal to C prime of x, and we find the value in that interval from 3 to 6. So in this value, so I guess I wouldn't have even had to go from -1 to 50. I'm going to go from like 2 to 7. So I'm going to go here, and I'm going to see I'm going to graph this. So I'm only looking on the interval from 3 to 6, so 2 to 7, I can see this part of the graph. Doesn't really tell me too much right now. What I want to do though is I have the C of x in my calculator. I'm just going to turn that off by clicking on the equal sign. And then I'm going to substitute in my derivative. My derivative was -10,000. I'm finding it over here. Over x squared. Plus, and then here's where you have to be really careful because this numerator was pretty crazy. So I'm going to put 2 parentheses, x plus 3, because I need to put the entire numerator in parentheses, 10,000 minus 10,000 x, close my parentheses for my numerator, divided by parentheses for my denominator, x plus 3, the quantity squared. I'm going to graph this, but I want to see where this is equal to 0. So I'm going to do one more on here, and I'm going to put y3 as 0. I'm going to graph this. Okay, this is really hard to see. So maybe my y max anymore, why don't I change that? Because I'm talking about a derivative of 0. I'm going to change this to like 10 or something crazy right now. Hey, we can kind of see it, that there's a 0 right here. And it looks like that's in the interval from 3 to 6. Second, calculate. You can either do 0 and do left bound, right bound, or because I put y equals 0 in there, I can do the intersection first curve. The second curve is y equals 0. I guess it's already close to it. I found this value that x would be 4.09807762. This is my final answer, so I can round it to 3 decimal places, so 4.098. This is my value of r, where this is true. And then, yeah, that's it for that part. And then the last one says, what is the greatest cost? Cost is anywhere the derivative is 0. Remember, we have to check to see what is the absolute max or the endpoints. So what you need to do is check what is C of 3, what is C of 9, and then I also want to check C of 4.098 because that was my 0. Okay, so then I say, I'm really glad I didn't delete this. So I'm going to get rid of that, I'm just going on the equal sign just in case I need it again. I'm going to highlight this equal sign up here. I'm going to do second, calculate the value. Oh, this is going to be way off the graph now. I'm going to go back up to when this was like 20,000 again. Second, calculate. The value at x equals 3, because that's one of my endpoints. And I can see it, I get 8333.333, just like I did before when I got C of 3. If I calculate C of 9, let me make sure, this says only 7 on here for x max, let me change this to 10. Function value at 9 is 8611.111. The value at, and this is where I'm going to use 4.098, and I'm going to use more decimals because this was not my final answer, so I want to check at 0762, and I get 8213.6721. What is the greatest cost? Well, and here, the greatest cost, this was a cost function, and it says where x is the order size in hundreds, so this is 300, 900, 409.8. Oh, sorry, you can't see this. I'm going to get better at this, I swear. 300, 900, 409.8. But I just want to know, what is the greatest cost? The greatest cost is going to be whatever is the biggest number here, which would be this one. And if you want to do that too, you can. If you want to keep it at 3, you can do that. A lot of times it will say if you have to round to something other than 2, or if they're like, hey, this is money, only 2 decimal places. But if you want to know for how much is this, it'd be for 900 bottles of Pepsi. And I think we're going to end there. I'll pick up more later. So this changed 132. This is now to 134. Thanks so much for being great. Yeah, I appreciate you. If you need anything, as always, please let me know.